Hello everyone, welcome to our differential equation class. In this video we introduce Sturm-Liouville problems. We are going to start with a brief review from the previous video where we solved simple eigenfunction problems, actually 4 of these eigenfunction problems, one with Dirichlet boundary conditions, one with Neumann boundary conditions, and 2 with mixed boundary conditions. Then we are going to see that these eigenfunction problems are particular cases of what is called Sturm-Liouville problems. Then we are going to see that these Sturm-Liouville problems have very nice properties. The solution of these problems have very nice properties, and we are going to then show that our simple eigenfunction problems, the solution of these eigenfunction problems, also have these properties. And today we are going to focus on one of these properties, which is that the eigenfunctions are mutually perpendicular or orthogonal. So we are going to introduce the idea of orthogonal functions, and then we are going to verify that the solutions of our simple eigenfunction problems are mutually perpendicular. So that's the plan for today. Let's start with a review of the solutions of the simple eigenfunction problems we solved in a previous video. So recall we studied the eigenfunction equation given by negative y double prime equal lambda y. So here this is the eigenfunction equation for the operator L of y equal negative y double prime. So we are solving the eigenfunction equation for this operator. We are solving this equation in the interval for the variable x 0l with boundary conditions at x equals 0 and x equals L. And the first boundary condition we studied is the Dirichlet boundary conditions, where we look for solutions of this equation, solution of y, and also the so non-zero solutions y and a number lambda, solution of this equation, where the function y must satisfy that vanishes on both sides of the interval. And we found that there are infinity many solutions. So given by lambda is given by n pi over L squared, where n takes values 1, 2, 3 up to infinity. And the corresponding eigenfunction for lambda n is yn, which is proportional, this is just a non-zero constant, proportional to sine of, and here is n pi x over L, and the L is the ground L. It should be this L. Okay, and these functions are called Fourier sine functions. We are going to discuss that later. There are infinity many eigenfunctions and eigenvalues for these Dirichlet boundary conditions. We also found solutions of the same equation for Neumann boundary conditions, and the Neumann boundary conditions say that the derivative of the solution has to vanish at 0 and L, not the function like in the Dirichlet problem. And we found that we also have infinitely many solutions given by lambda is the same as before, n pi L over L squared, but instead of sine we have cosine for the eigenfunctions. N is still taking values 1, 2, 3 to infinity. So this part of the solutions is very similar to in the solution in the previous problem, just changing sine by cosine. Cn is an arbitrary constant, non-zero constant. But here in the Neumann problem we have one more solution, this one here, which is we also have lambda equals 0 for this problem. Lambda equals 0 is a solution for Neumann boundary condition, but lambda equals 0, so lambda equals 0 is not a solution for the Dirichlet problem. So lambda equals 0 is a solution for the Neumann problem, and the corresponding eigenfunction for lambda equals 0 is a constant, a non-zero constant. Recall, all these constants cannot be 0. We also solved the same differential equation with mixed boundary conditions, where in the first boundary condition we look for solution where the function vanishes, and in the second boundary condition the derivative vanishes. And this is what we get. We get that now the eigenvalues are different, and then the eigenfunctions, here n is again 1, 2, 3 up to infinity, are sine functions of the square root of the eigenvalue times x. And lastly, we solve this problem with the second type of mixed boundary conditions, where the derivative must to vanish in the first boundary condition and the function has to vanish in the second. So the derivative is here. Here the derivative was in the second condition. And we got the same eigenvalues as in the previous mixed boundary value problem, but now the eigenfunctions have a cosine instead of a sine and takes the same values. So these are the 4 simple eigenfunction problems we solved in the previous video. Now let's introduce a general type of problems called Sturm-Liouville problems. There are several versions of these problems. We are going to focus on the one called regular Sturm-Liouville problems. And the reason we are interested in this type of problem is because the eigenfunction problem we solved in the previous video, so this eigenfunction problem, negative y double prime equal lambda y, with boundary conditions either Dirichlet or Neumann or mixed boundary conditions, this type of problem is a particular case of a more general eigenfunction problem, which is called precisely Sturm-Liouville problems. To introduce Sturm-Liouville problems, the first thing we need to do is to introduce what is a Sturm-Liouville operator. A Sturm-Liouville operator is an operator of this form here, where the function p is a differentiable function that is positive. We have a negative sign on the front, but the function p is positive for all values of the variable x in some interval where we are working, so in this case interval ab. The function q is a continuous function, and the operator acts on function y that is twice differentiable, so because we have a second derivative of function y. So an operator with this form is called a Sturm-Liouville operator. Notice that we can expand this, distribute this derivative in this product, and we can get the derivative acting here, so a second derivative of y times p, which is this term, and then another term when the derivative acts on the function p, and that would be this term here, and then we still have the term with q. So from here we see that L of y is nothing more than some function a2 that we chose to call negative p times y double prime plus some function a1 y prime plus some function a0 y. Notice that this is the form of the most general second order linear differential operator, and in the particular case where the function a1 is the derivative of a2 and a2 is negative, because I'm not writing this negative sign explicitly, when this function is negative and this function is the derivative of this function, then we have a Sturm-Liouville operator. So a Sturm-Liouville operator is just a particular case of a second order linear differential operator with these conditions. An example of a Sturm-Liouville operator is, of course, the operator we were working in the previous video, negative y double prime. This is a Sturm-Liouville operator, and is probably the simplest Sturm-Liouville operator because we need to choose here the function 1 and here the function 0. P is 1, Q is 0. This operator is very important to us because in the next video we are going to see that this operator appears when we try to solve the heat equation, and also appears when we try to solve the wave equation and many other important equations in physics. Other cases of Sturm-Liouville operators are, for example, the Legendre equation that appears when one tries to solve the equation for electromagnetism in the case of spherical symmetry. Then the same equations, the equation of electromagnetism but with cylindrical symmetry, take a different form that is called the Bessel equation. Both of these equations are particular cases of Sturm-Liouville operators. Perhaps more famous example is the time-independent Schrödinger equation that is the backbone of quantum mechanics. Well, the Schrödinger equation in the case of time independence is a Sturm-Liouville operator. So many equations in physics are Sturm-Liouville operator. Many equations in physics are written in terms of Sturm-Liouville operators. So now, what is a Sturm-Liouville problem? Well, it's an eigenfunction problem for a Sturm-Liouville operator. So a regular Sturm-Liouville problem for a Sturm-Liouville operator L of y. So this L of y is a Sturm-Liouville operator, is to find eigenvalues lambda and eigenfunctions y of x, solution of this eigenfunction problem. The Sturm-Liouville operator proportional to y, acting on y proportional to y, and with these boundary conditions, which are homogeneous boundary conditions, and they include Dirichlet boundary conditions, or Neumann boundary conditions, or mixed boundary conditions of one type or the other type. So this is a Sturm-Liouville problem, and it's possible to show that the solutions of Sturm-Liouville problems with L, a general Sturm-Liouville operator, they have very nice properties, and the properties are summarized in this result. Suppose we have a regular Sturm-Liouville problem given by a Sturm-Liouville operator equal lambda y, acting on y equal lambda y on some interval AB, and we have these general boundary conditions that includes all the boundary conditions we are interested in. So this regular Sturm-Liouville problem has solutions given by eigenvalues and eigenvectors. We are going to write them in this way. And these eigenvalues and eigenvectors have the following properties. They have a lot of properties, and we are really interested in these properties. The first property is that we kind of assume it, but actually it's an important property. All the eigenvalues lambda n are actually real valued. So first property. Second property, if we have two eigenvalues which are different, eigenvalues of the Sturm-Liouville problem, then the corresponding eigenfunctions are perpendicular. So this symbol here means orthogonal or perpendicular. Recall, these are functions, and we have example of how this function looks like. For example, in the case of this simple operator, we are talking about these functions here. These functions for different values of n, we are saying that they are perpendicular. So what does it mean that two functions are perpendicular? Well, a big part of this video is going to be to try to understand this property. So we leave it here, and we keep going listing the properties, and then we come back. Another property that the eigenvalues and eigenfunctions have for Sturm-Liouville problem is that there is a smallest eigenvalue, what we can label lambda 0, and then all the other eigenvalues are different, and they are actually larger than lambda 0. Then we have the next eigenvalue lambda 1, the next is lambda 2 is larger than lambda 1, and so on. And we have this property as that all the eigenvalues go to infinity as the label goes to infinity. So they are ordered. They can be ordered, the eigenvalues. And the next property is that if we label the eigenvalues with this index that we start at 0, and then 1, 2, then the corresponding eigenfunctions have n zeros on the interval AB. For example, the eigenfunctions y0 has no zeros. The eigenfunction y1 has 1 0, and so on. And also these eigenfunctions are unique except for a multiplicative constant. We are going to see what do we mean in an example pretty soon. And the last property, and one of the most important property that we are going to study in the next class, is that if a function f of x is any continuous function on the same interval where we solve the eigenfunction problem, then this function f of x can be written as an expansion of constants, coefficients, times the eigenfunctions of the Sturm-Liouville problem, this eigenfunction here. And we have a formula for the coefficient given by these integrations here, which again we are going to study these formulas in the next video. So an eigenfunction problem, a regular Sturm-Liouville eigenfunction problem, has solutions, and they have all these properties. So the proof of part of the proof of this statement is in our textbook. Essentially all the properties up to property D. Property E, we give a reference where you can see the proof of that. Property B will be explained later. Recall, property B is this property of orthogonality that we need to go over that later. And property E, the property E is this expansion property, will be discussed in the next class, in the next video. So what we are going to do now is we are going to verify that the solutions, for example, of the Dirichlet problem that we found for this simple operator, so the solution we found in the previous video for this eigenfunction problem with Dirichlet boundary conditions satisfies actually properties A, C, and D, which are A, C, and D. So the eigenvalues are real. Well, we know that, but we are going to put it in writing. Then the eigenvalues can be ordered, and then the zeros of the eigenfunctions. Let's see that the solutions we already found satisfy those properties. So this is our first example. So let's recall solution. Let's start here, solution. So we found, let's recall, we found in a previous video that the solution of the eigenfunction problem that we wrote over there. So recall the eigenfunction problem is y double prime plus lambda y equals 0 with Dirichlet boundary conditions, which are y at 0 equals 0 and y at L equals 0, are given by, recall, lambda n was n pi over L square, and then the y-n's were functions that they are proportional. The proportionality constant has to be different from 0 to sine functions of the argument n pi x over L, and here n started with 1, 2, 3. This is the n we are using our label. Okay, the first thing we see here is that these solutions satisfy that all the eigenvalues are real, so they are real. Okay, Next property. So there are infinity many eigenvalues, and they are because n goes to infinity, so that is satisfied, and they can be ordered like this. Okay, and the eigenvalues go to infinity as the label goes to infinity. Well, our label here n starts at 1, and here we need to start at 0, so we need to do a very simple relabeling, very simple. So we relabel this is horrible. We label the index n is now gonna be m plus 1. Okay, so now when n is 1, then m starts at 0, and then 1 to infinity. Okay, and with that, lambda n, which is n pi over L squared, now is going to be lambda m, and n is now m minus 1 pi over L squared. So with the index m, it looks like that. M plus 1, sorry. The only thing I'm doing is I'm replacing n by m plus 1, so it goes there. All right, so when m is 0, we start where we started before, at n p over L squared. And then what else? Well, now we can see that lambda 0 with a new label, lambda, let's put it like this, m equals 0, what is going to be? It's going to be pi over L squared. Okay, what is lambda m equal 1? Well, when we put a 1, then we have a 2, the square makes a 4, so it's going to be 4 pi over L squared. Obviously, it's bigger, so satisfy that inequality. And what is lambda m equal 2? Well, we have to put a 2 here, so we have a 3, so we have a square, so it's a 9 pi over L squared, and obviously is bigger than the previous one, and we can keep going like this. So yes, that property is satisfied. So this property here is satisfied. Property C. And now if we use that label, the label m, we can see that if we use this label m that starts in 0, we can see that ym now has m zeros on the interval ab. Well, the interval is actually is going to be 0. It's going to be 0 L where we are working. Okay, let's see that. Well, the only thing we need to do is we need to write ym of x, and ym is proportional to a sine function of m plus 1 pi x over L. But first, let's see here one thing, that this constant here cm is a multiplicative factor, isn't it? Multiplicative factor. Well, this is what we are saying here. It's unique up to a multiplicative factor. So that is what we mean by that. And what about the zeros? Well, here we have a little picture of the first three functions, m equals 0, m equals 1, m equals 2. At m equals 0 is a sign that vanishes only at 0 and L. But if you put n equal 1, so with a 2 here, you're going to see that actually vanishes halfway. And then if we increase m, it has 2 zeros actually, and it keeps going like that, higher and higher frequency with more and more zeros given by this property here. So that is also satisfied. And and we can give an exercise, for example, and show that the same three properties are satisfied not only by the solution of the Dirichlet boundary condition problem, but also with Neumann, and the mixed boundary condition satisfied also all these properties. In the rest of this video, we are going to focus on property B of the solutions of eigenfunction problem for Sturm-Liouville operators. If we have two different eigenvalues, the corresponding eigenfunctions are orthogonal or perpendicular. So in the case of this Sturm-Liouville problem, what this property says is that two sine functions with different values of the label n are perpendicular. What does it mean to have two functions that they are perpendicular? So let's do a brief overview of orthogonal functions, and one way to start is with orthogonal vectors. Recall that in space, if you have two vectors, the vector u and a vector v, they are going to be perpendicular, vector v, if the angle in between is 90 degrees. One way to characterize analytically that this is happening is with the dot product of the two vectors. Recall how we introduce the dot product of, or how we define the dot product of two vectors in space. Well, if you have the components of the vector, you do the sum from I equal 1 to 3, because we are in space, of the component ui multiplied by vi, and you add up all these multiplications. Recall this is for vectors u and v with three components, so they belong to R3. So you introduce this dot product, and then you can prove a theorem that says that the vectors u is going to be perpendicular to the vector v if and only if this dot product, the dot product of u with v vanishes. So this is one way to characterize vectors or orthogonal vectors when you have the vectors given in components and you don't have the picture in space. So you do this calculation and the dot product, and if they are 0, then they are perpendicular. So what we are going to do, we are going to now translate this concept of orthogonal vectors to functions. So we are going to define orthogonal functions, and in order to do that, we need to generalize the dot product, this dot product, from vectors to functions. There are many generalizations. We are going to introduce one of the possible generalizations, and this is called an inner product. And here it is. The inner product of two functions, f and g, these functions are defined on the interval ab. It's going to be, this is the notation, and it's going to be the integral between a and b on that interval of the product of f and g. So first of all, this definition is a generalization of the dot product for vectors. Recall, the dot product for vectors is if you have the vector u given in components. So for example, let's write the vector u in components. U is the vector u1, u2, and u3. These are the components of the vector, and suppose you have the vector v, that is a vector with component v1, v2, and v3. Okay. So what is the dot product? Well, we said the dot product of vector u with vector v is going to be u1 v1 plus u2 v2 plus u3 v3. A nicer way to write that is to say that this is the sum, as we did before, the sum from I equal 1 to 3, this is u dot v, of the component u, I, vi. Well, we just said that we introduce the dot product of, or the inner product of two functions as the integral from a to b of f of x, g of x, dx. Well, you can see that this is a generalization of the previous dot product, where the component of one vector is replaced by the values of the function at any point in the interval. The component of the other vector is replaced by the values of the other function on the interval, and then the sum is now replaced by an integral. So this is a simple generalization of the dot product from vectors to functions. And it's a good generalization because the dot product for vectors has three important properties: positivity, symmetry, and linearity. And these three properties are also transferred to the inner product of functions. The inner product of two functions, this inner product has the positivity property, which means the dot product of a function with itself is never negative, and if it's zero, the only case that happens is with f equals 0. Symmetry, you switch the order, nothing happens. Linearity, you can distribute this dot product, and it's very easy to see that you can do it with this definition, because it's just an integration and a multiplication, so it has the linearity property. So this is a good dot product, and with this dot product we can introduce the norm of the magnitude of the length of a function, in the same way we define the length of a vector. If we have a function f of x on the interval ab, we can define the magnitude or the length or the norm of the function as the dot product of the function with itself, square root. This is not a problem because of the positivity property. The square root is gonna be always give you a real number, and this is nothing more than the integral from a to b of the function f of x squared dx, and then we compute the square root. So once you have the definition of the length of the norm of a function, then you can introduce unit functions. A function is going to be a unit function u of x, if it satisfies that its length is 1. And recall, the function does not need to be 1. What it has to be 1 is the integral from a to b of u of x squared dx square root. So this integral is the integral that has to be 1. And now, if you have a function f of x and this function is not unit, then you can always rescale the function by dividing by, this is a number. Recall, this quantity here is just a number. When you do the integral, you get a number and then the square root. So you rescale the original function by that number, and then the this function u is going to be a unit, and of course proportional to the original function. Now there is no geometrical interpretation of in R3 of the dot product. So if we want to talk about perpendicular function, a function f of x perpendicular to g of x, we cannot use any picture in R3. So what we do is we use this property that we have proven for vectors. We use this property as a definition for functions. And now we are going to say that two functions are, this is a definition, not a theorem now. Two functions are perpendicular if and only if the dot product of these two functions vanishes. So this is how we introduce the concept of orthogonal functions. Let's see how we can verify that two functions are perpendicular or not. For example, here we have, we need to show whether that this function, the function x and the function x squared on the interval -1, 1 are actually perpendicular, but the function x and the function x cubed, they are not perpendicular on the same interval. So let's see how we do this. So solution, what we need to do is we need to do a dot product, and the dot product is of, we're going to start with the function f dot function g. And what is that? Well, this is the integral on the interval we are working. Recall we are working on the interval -1, 1. So between -1 and 1 of the function x multiplied. So what we need to do is the function f of x multiplied by the function g of x. That's all we need to do, an integral. Okay, if we do that integral, this is going to be the integral from -1 and 1 of the function x multiplied by the function x squared dx, which obviously is nothing more than the integral between -1 and 1 of the function x cubed dx. All right, so what is that? Well, that is nothing more than x power 4 over 4 evaluated at -1 and 1, but this is 1/4. Then we have x power 4 at 1 is 1 minus -1 power 4, which is going to be positive 1. So this is nothing more than 1/4. 1 minus 1, so it's 0. So the function f dot g is actually 0, and the functions are by definition perpendicular. So one way to say that is function x is perpendicular to function x squared on the interval -1, 1. On a different interval, things are different. So what about the other calculation? Well, f dot h. Now, what is that? It's the integral from -1 to 1. Now the function f of x, h of x dx. What is that equal to? Well, it's the integral between -1 and 1. F was the function x, and h, what was the h? X cubed dx. We do the same calculation as before. This is just a product, so nothing interesting going on here. We get the x power 4. Let's do a better 4. X power 4. It was worse. Power 4 dx. And then this is nothing more than x power 5 over 5. But if we do the same calculation we did before, evaluated -1 and 1. So this is 1/5, and then we need to put 1 to the power 5, which is 1, minus -1 to the power 5. But that is -1, so we end up with 1/5, 1 plus 1. So f dot h is actually 2/5. It doesn't matter what is the actual value. The important thing here is that the function x is not perpendicular to the function x cubed on the interval -1, 1. And that's that. So the verification is a simple calculation. So in general, if you do this calculation for many powers, you're going to realize that the polynomials 1, x, x squared, x cubed, and so on are not mutually orthogonal. Some are orthogonal, for example, x on this interval. No? This is orthogonal to this one, but they are not orthogonal here, and in general, they are not going to be all of them mutually orthogonal. The fact is, we are going to see later that is actually very important for what we want to do, to have a sequence of functions that they are all mutually orthogonal. Our last example for this video is to verify that the eigenvalues lambda n and eigenfunctions yn, solutions of the Sturm-Liouville problem this Sturm-Liouville problem with Dirichlet boundary conditions satisfies the property of property B in the Sturm-Liouville theorem, and also find unit eigenfunctions. Okay, so what is that? Well, recall the property B is the property we are studying if we have two different eigenvalues, the corresponding eigenfunctions are perpendicular with the definition of perpendicular we introduced before. We know for this eigenfunction problem with Dirichlet boundary condition that these are the solutions. There are infinity many solutions, yn, given by any constant proportional to these particular sign functions, and these are the eigenvalues. Okay, instead of working with our arbitrary constants here, we are going to choose them all to be 1, and we are going to work with that. So let's choose the constant Cn, just to simplify the calculation, so we don't carry all these constants Cn equal 1. Okay, so then what do we need to do? Well, then in that case the eigenfunctions look a little bit nicer. Then yn of x, they are simply sine functions, sine of n pi x over L. So you see we have for larger values of n, we have higher and higher frequency in the sine function. Okay, so what do we need to do? We need to grab two arbitrary eigenfunctions, for example the eigenfunction yn, and compute the dot product with ym, which is nothing more than the integral. Here recall we are working in the interval 0L. This is on the interval 0L. So we need to do the integral from 0 to L of the function yn, which is just a sine of n pi x over L, and the function ym, which is a sine of m pi x over L dx. And recall here we are assuming that n is different from m, because we want different eigenvalues to verify that they are perpendicular. Okay, so what do we do here? We have a product of two sine functions. So whenever you have products of two sine functions, it's very useful to have trigonometric identities, and here is the one trigonometric identity we can use. The sine of A multiplied by the sine of B. What is that equal? Well, that actually is equal 1/2, and then the cosine of the addition, actually of the difference first, A minus B, minus the cosine of the addition, A plus B. It's a trigonometric identity, you can prove it. We are just going to use it. If we use it, what do we get? Well, we get that yn dot ym. So this is the key to do the integral, that trigonometric identity, because now we are going to have 1/2 outside, and now we are going to have two integrals, one for this cosine and one for that, and here A is that and B is that, isn't it? So we are going to have the integral from 0 to L of a cosine of the difference. Notice that okay, let's write it down somewhere. We are going to use this this identity with A equal n pi x over L, and B is going to be obviously m pi x over L. Notice that the A and B are almost identical. This part is identical. The only difference is n and m. So when we do the difference, we can pull common factor, all that is common, and we get n minus m, let's go back to blue, n minus m multiplied by pi x over L dx, and then we have the other term that has a negative sign, so negative 1/2 integral from 0 to L, again is a cosine, but now is n plus m pi x over L dx. So that's the integral we need to do, but it's an integral of a sine and a cosine. So, and recall in the first integral and in the, well, let's recall, m is different from n, so this is never 0. And the other thing is that both n is positive and m is positive, so this is also never 0. So we can divide by those quantities. So if we do that, we get, let's integrate 1/2. What is the integral of the cosine? Well, is the sine function. So we are going to have the sine function. Oh, I got lost. What I was saying? Yes. So we need to integrate this cosine function. So what the function gives me a cosine, a sine, and then we need to do L over n minus m pi. So we flip the coefficient in front in the argument of the cosine, then is a sine with the same argument, n minus m pi x over L, and that has to be evaluated at 0 L. One more time, we can do this calculation because the denominator is never 0. And then we have minus, let's put it here, minus 1/2, and now we have the integrate this other cosine, which is going to be L. So we flip the constant in the cosine, so L over n plus m pi, and then we are going to have a sine of n plus m pi x over L, all evaluated at 0 and L. And you can verify that this is correct because if you compute the derivative of the sine is going to be the cosine, and then we are going to have an n minus m pi over L, but that is going to cancel that, and this is going to cancel that, this is going to cancel that, and you're going to get only the cosine. So yeah, we did it right. So what do we do now? We do the evaluations. So let's move on to this little page. So we have yn dot ym, the dot product, and then what is that going to be equal to? So in the first term we have L over 2 n minus m pi, and then when we do the evaluation, what do we get? We get sine of n minus m, which is an integer, pi x over L, or pi, like this. When I put L here, they cancel out, and then minus at 0, but sine of 0 is 0. So we have that, and then we have minus L over 2 n plus m pi sine of n plus m pi x over L. Oh, we need to evaluate at L minus at 0, which is 0. Okay, so one last comment. It looks like a complicated expression, but actually this is nothing more than 0, and this is nothing more than 0, because the sine of any nm, so a multiple of k pi is always 0 for k equal 0, plus minus 1, plus minus 2, so on. So 0. What we conclude here is that yn dot ym, they are 0. So the what happened here? So the eigenfunctions are mutually perpendicular whenever m. So this is equivalent because by definition that yn is perpendicular to ym for any two n and m different. So they are all mutually perpendicular. All sine functions, any of these sine functions is perpendicular to all the others. The only thing we need to do now is to compute how big are these functions, the norm of these functions. So let's compute the length square of yn, which is nothing more than yn dot yn. So we need to do the same calculation, but now with the same value of n. So yn dot yn is nothing more than the integral from 0 to L of a sine function, sine square of n pi x over L dx. And now we need another trigonometric identity because we have this sine square, and I need to fix this because it's horrible. So what identity we are going to use? Well, here is one that is pretty good for this calculation. The sine square of any argument is 1/2 1 minus the cosine of twice that argument. So if we use that identity in our calculation, what do we get? Yn dot itself is 1/2 now the integral from 0 to L of 1 minus the cosine of 2n pi x over L dx. So we need to do two integrals. The first term, the integral in the first term, well, we have the 1/2 outside. We integrate the first term. What is going to be? It's going to be the function x evaluated at 0 and L. And on the other term, what derivative gives me a cosine? Negative sign. Sine. Sine gives me a cosine. What did I do here? Yeah. So yes, I'm integrating also a cosine. So what function the derivative gives me the cosine? Well, the sine. So sine of 2n pi x over L. But if I derivate the sine function, I'm going to get the cosine, but then I'm going to get 2n pi, so I'm going to get 2n pi over L. So I need to divide by the 1 over that, so L over 2n pi. And that has to be evaluated in 0 and L. Okay, so from the first term we get 1/2 L minus 0, and from the second term L over 2n pi, we get sine of 2n pi. When I put x equal L, then they cancel out, minus at x equals 0 is 0. And again, as before, this sine function evaluated at multiples of pi is 0. So one more parenthesis, which is this parenthesis here. So we end up with L over 2. it doesn't matter. So the important thing is that the dot product of yn with itself is a constant that is independent of n. It doesn't matter which eigenfunction you choose. All the eigenfunctions have the same length, and that is this implies that the length of yn does not depend on n and is nothing more than the square root of L over 2. So how do we get unit eigenfunctions then? Well, unit eigenfunctions are going to be the original eigenfunction yn of x, and now we need to divide by the length of yn. But we just compute the length. The length is square root of L over 2. We need to divide by that. Then the eigenfunctions un of x, the unit eigenfunctions are going to be 2 over L square root sine of n pi x over L. And these are the unit eigenfunctions for the Sturm-Liouville problem for our operators with Dirichlet boundary conditions. So as an exercise, you can actually try to do a similar calculation for the other eigenfunction problems. Not the Dirichlet, but also the Neumann and the mix boundary condition problems, and find what are the length of those vectors, find unit eigenfunctions for all these problems. If you do that, this is an exercise, just do it, and if you do that, this is what you are going to get. For the four eigenfunction problems, recall we are working with this eigenfunction problem on 0L, and the boundary conditions are on 0 and L, of course, and we just did the Dirichlet problem, and we found that these are the unit eigenfunctions. What is this here? Nothing, so this shouldn't be there. So these are the eigenfunctions, the unit eigenfunctions, and these are the eigenvalues that we found before. These also are called sign eigenfunctions. These are normalized, length 1. And here we have the result for Neumann. For Neumann, the length is going to be the same as for Dirichlet for the eigenfunction with n equal 1, 2, 3, infinity. But recall, Neumann has also eigenvalue 0. And then the unit eigenfunction is actually square root of 1 over L, not 2 over L, only 1. Just do the calculation and you're going to see that this is the correct unit eigenfunction for lambda equals 0. And these are the unit eigenfunctions for the other eigenvalues. And then you have the mixed 1 and the mixed 2. That notice that all the problems have the same normalization factor. The same normalization factor except the eigenfunction 0 for Neumann. All the others have the same normalization factor. So these are the normalized eigenfunctions for our 4 eigenfunction problems. This is a good place to stop. See you guys in the next video.